I'd like to begin by thanking the organizers for giving me the opportunity to talk here, and it's a pleasure to be visiting Korea again. I'm going to be giving a very simple talk. It's going to be based on recent work with Chi-Ming Chang on 1/16 BPS states in n=4 super Yang-Mills theory in 4 dimensions. This is a problem that has been around for a number of years by now. Here's a presumably incomplete list of some of the people who have been thinking about this problem, have worked on this problem. And in this talk, I'm going to be adding epsilon to what has been done by these people. Why is counting 1/16 BPS states in n=4 super Yang-Mills an interesting problem? That's because there are large 1/16 BPS black holes in ADS5 supergravity, as we know. I apologize here for missing 2 names, Kanduri and Lucetti, who, along with Real, had found the most general known 4-parameter family of 1/16 BPS black holes in essentially ADS5 times S5. To try to understand the Bekenstein-Hawking entropy of these large 1/16 BPS black holes from the gauge theory perspective is an interesting problem because it appears to be, I mean, if this works, it would appear to be richer than the previously known and successfully counted microscopic entropy of BPS black holes, for the reason that it would seem that the whatever entropy that counts these BPS, entropy that counts the microstates of these BPS black holes will know about the dynamics of the gauge theory. In particular, the entropies, it is known that the entropy of such black holes cannot be accounted for by simply computing the superconformal index of the gauge theory. It appears to be, if you do that, you'll get a too small answer, presumably due to the large amount of cancellation between BPS states that will contribute to the same term in the index, but with opposite fermion number. Neither could one reproduce the entropy of these black holes from the free n=4 super Yang-Mills theory. You get entropy that's slightly too large. And one expects that the interactions of gauge theory should reduce the number of BPS states. We're going to be investigating this counting problem of 1/16 BPS states in weakly coupled n=4 super Yang-Mills theory, following the approach of Grant, Grassi, Kim, and Minwala a few years ago. And here on this slide, I summarize the main results or claims that I'm going to make. First of all, we'll identify the complete spectrum of 1/16 BPS states in the infinite n limit. By that, I mean BPS states of fixed conformal dimension in infinite n limit. The result will match precisely with the BPS multi-graviton states in ADS5 times S5. I should mention that this part of this was, of course, understood before, but only within some subsectors, such as the sector involving operators made out of scalars only. But here, I will do it to full generality. And that small improvement will buy us something because it will allow us to kind of try to explore all possible operators of this sort. And that will be important for reasons that become clear later on. Then I'm going to make a somewhat bold conjecture, and by the end of the talk, you might try to prove or disprove what this conjecture, that all 1/16 BPS states at finite n=4 super Yang-Mills theory are of the multi-graviton form, quote unquote. I will describe what I mean by operators in n=4 super Yang-Mills of the multi-graviton form in a moment. And I'll provide some limited evidence for this conjecture through a brute force computer search of cohomology classes. If the conjecture is correct, it would imply a problem, that is, there are not enough states in n=4 super Yang-Mills, at least in the weakly coupled regime, to account for the Bekenstein-Hawking entropy of these large BPS black holes in ADS5. And I'll comment on this puzzle towards the end of the talk. Okay, I'm going to now formulate the counting problem of 1/16 BPS states Most of this was well known on the slides, and as I mentioned, I'll add epsilon towards in a few slides to what's already known. So we want to find all 116 BPS local gauge invariant operators in n equals 4 super M-Mills theory in 4 dimensions, or equivalently, radial quantization 116 BPS states of the theory on 3 sphere. We'll pick one out of the 16 supercharges. I'll call it Q. Of course, as you probably all know, the set of supercharges of n equals 4 super M-Mills are in the 4 of SU4R symmetry, carries also a chiral or anti-chiral spinor index. And by this Q, I'll choose this Q to carry some particular charge, some definite charge with respect to Cartan generators of, say, SO6R symmetry, and one can carry some particular spin with respect to one of the left or right SU2 angular momentum with respect to the rotation in 4 dimensions. In radial quantization, the Hermitian conjugate to Q is a special superconformal generator, which I'll denote by S. The problem of counting 116 BPS states is the same as the problem of counting states in radial quantization that are annihilated by this particular Q and S out of the 16 copies of them. By the standard Hodge theory argument, this is equivalent to the problem of counting Q cohomology. Here, Q is an operator that squares to 0. That's the problem of counting Q cohomology is much easier than counting, actually writing down states are annihilated by S because the action of Q on the fundamental fields are exact, whereas the action of S receive complicated quantum corrections in general. Okay, so for this problem, it suffices to consider gauge invariant operators that are made out of product of traces of fundamental fields and their covariant derivatives, which I refer to as letters. And it suffices to work with the letters that are, in some sense, 116 BPS in the free theory. So there is a BPS bound that states that the energy or conformal, or the conformal dimension of the operator E is greater than or equal to twice J left, which is the, let's say, the third component of the left SU2 angular momentum, or SU2 spin of the operator, plus the sum of the 3 Cartan generators of SO6. With the appropriate choice of Q, as on the previous slide, the 116 BPS states will saturate this BPS bound. Clearly, if you want to have a chance of writing down any local gauge invariant operator to be 116 BPS, you better use the letters that already saturate the bound. Otherwise, you can never obtain BPS states by multiplying these letters together. Now, as in the kind of standard notation of the fields in n equals 4 super M-Mills, there are 6 scalars which are denoted by capital phi. This phi has upper, in my convention here, has upper index, which you can write as I and j. It will be anti-symmetric I and j. Ij run from 1 to 4. Here I've chosen a specific one, which is, I mean, all of this depends on the convention for my charge Q, which I did not write explicitly on the previous slides, but the details are not, of the convention are not too important here. Suffice to say that in some convention, the 116 BPS letters are the following form. You take phi upper 4n, where n, these two indices I and j originally run from 1 to 4. You take the first index to be 4, this second index to be 1, 2, or 3. So these give you 3 scalars, which you call phi upper n. Then there's the non-abelian field strength, F, which is a 2 form, of course. And I write the 2 form as a tensor with 2 chiral spinor or anti-chiral spinor indices. So here, the plus refers to the index, the alpha and beta, the chiral spinor index, which I have chosen them to be plus, so that each of these plus subscript contributes 1/2 to this j left, and the total F++ has j left equals to 1 and E equals 2, and therefore it saturates this BPS bound. And this I denote by a little f. The other components of the field strength would not have this property. There are 5 fermionic letters constructed out of the fermion psi, which is the Dirac fermion in the 4 of SU4. So here I've taken this n stands for the SU4 fundamental index, which is taken again to be 1, 2, or 3, and this plus refers to a chiral spinor index, which is taken to be plus, so that this J left 3 eigenvalue is plus 1/2. And this I denote by little psi n. And then there's the conjugate guy, where I take the SU4 R symmetry index to be, this is in the anti-fundamental representation. I take that index to be 4, and there's a anti-chiral spinor index, which I call alpha. Usually I should really write alpha dot, but I didn't want the dot to float everywhere in the notation, so I will just write alpha here, but every time I write alpha on these slides, it's really referring to a anti-chiral spinor index, and that's this lambda alpha. So there are 5 fermionic letters that saturates this BPS bound. And in addition, there are 2 covariant derivatives. So these D covariant derivatives are D with subscript mu, the Lorentz index, and I trade mu with alpha beta dot, and I choose the chiral spinor index to be plus, and the anti-chiral spinor index, alpha, is free. So I call this, in the shorthand notation, just D sub alpha. It's just 2 out of the 4 ordinary gauge covariant derivatives. And these are the quantities that I'm going to use to construct these 116 BPS operators. There are a little bit of constraints among these letters. First of all, of course, the commutator of these covariant derivatives are the field strength that's given by this relation. And then there's one single non-trivial equation of motion among these letters, which is the equation of motion for lambda alpha of that form. It's not too hard to take care of these relations by introducing the following generating functions or generating operators. For example, I can take these phi n's with arbitrary number of covariant derivatives I count them, symmetrize with back to their spinor index, and write this generating function or generating operator. The reason I prefer to work with this phi n of z rather than derivative action of phi n is because here the d alphas are automatically symmetrized. Here this z upper alpha are just some ordinary commuting bosonic variable. Because anytime I have a commutator anti-symmetrized epsilon alpha beta can try with this d, I can just replace with f, and that will be taken into account separately. And similarly, I define analogous expression phi n of z and f of z, and then I can reproduce independent operators involving derivatives acting on these guys by just taking the derivatives, but just by taking the coefficients of the expansion of these generating functions in z. And I can also define a lambda z with no spinor index floating around in this way. So here, you see that the spinor index on these d alphas, as well as spinor index of lambda beta, are all symmetrized. This is so that this combination, this equation of motion for lambda alpha, will not be counted. So if you have some expression involving covariant derivatives acting on lambda beta, can try with epsilon alpha beta, epsilon upper alpha beta, then you get some expression like this, and you can use the equation of motion to replace that d alpha lambda upper alpha by a commutator of phi n and psi n, and at the end of the day, you can write all the gauge invariant operators by simply taking, say, the trace of products of the coefficients of these 4 generating functions in Z. Now I'm going to go one step further and introduce a anti-commuting generating parameter, which we call theta n, where n runs from 1 to 3 as before, and form this kind of superfield-like object, capital psi z theta. Let me remind you that there's z alpha. There are 2 z's, which I call z plus and z minus. And then there are 3 thetas, which are fermionic, odd parameters. And it's a combination of these lambda and theta phi n and theta n, theta m, psi p, and finally theta cubed fz. Let me emphasize that now this expression is entirely unconstrained by the equation of motion, except for that psi, if you set both z and theta to 0, then this psi vanishes. That's because this lambda, by definition, vanishes as z equals 0. Okay. Now, what you buy by writing down that superfield is such that the action of this supercharged Q I've chosen now takes an extremely concise form, as basically as simple as it can possibly be, which is Q acting on psi of z is equal to psi of z squared. You can check this. I mean, there's some coefficients you have to massage a little bit, depending on the convention, but at the end, this is what you find. And the psi of z is only subject to the constraint that psi at 0 is equal to 0. So now, all the gauge invariant operators of zero twist. By zero twist, I mean the classical dimension minus 2j left minus h1 minus h2 minus h3 is equal to 0. They are made out of products of derivatives of this generating field psi of z with respect to z, capital Z, either z or little z or theta. And then you set this z and theta to 0. You get all the operators that you have. And the problem now amounts to computing Q cohomology on the space of all such operators. And here's the claim. In the infinite n limit for any operators of fixed dimension, the Q cohomology classes are represented by products of single trace operators of this form. So let me explain this expression. So here I've got a single trace. I can take products of these. I just write one trace. Inside the trace, you have products of only one derivative acting on psi. You can take it to any power, multiply them. And outside the trace, you can act with arbitrary number of derivatives on z and on theta. Now, let me remind you that z is a bosonic variable. So partial z psi is odd. So this k beta can only take value 0 or 1, whereas m of k can be any non-negative integer. Whereas here, partial theta is odd, so Qn is 0 or 1, whereas P alpha can be any non-negative integer. And these are all the operators you have. Of course, you would expect some relations among these operators. Sometimes you may be able to switch around the partial derivatives outside the trace and inside the trace, but that counting problem can be solved without too much work, and you can write down a generating function that counts all such operators. And the result precisely agrees with a known generating function that counts the free 116 BPS multi-graviton states in ADS5 times S5. So that completely solves the counting problem. I should have said that this operator is easy to see why they are Q closed. If you take Q acting on this guy, Q acting on psi gives you psi squared. So Q acting on partial derivative psi. If you have only one derivative, you get commutator or appropriate anti-commutator of psi with this thing. And when Q acts on everything inside the trace, by 6 of the trace, this thing is Q closed. And you can convince yourself that operators of this type will not be Q exact, and they indeed give rise to non-trivial Q cohomology classes, at least in infinite n limit, where you can ignore trace relations. Now, let me comment on what happens at finite n. At finite n, you expect that there are trace relations among the operators that describe the multi-graviton states in the infinite n limit that I wrote in the previous slide. That's, of course, not surprising. So there could be some relations. Maybe some of these operators I wrote in the previous slide will just vanish. That's OK. I'll refer to all such operators still as quote-unquote multi-graviton operators, even at finite n. The question is then, are there new Q cohomology classes that are not of this form due to trace relations? It could be that you have some operator which is not Q closed at infinite n, but maybe at some small values of n, it becomes Q closed because Q acting on this operator gives you some trace relation that vanishes by the trace relation. Well, in fact, initially, the motivation of this project is to find these new Q cohomology classes because we thought that the black hole states cannot be accounted for just by these multi-graviton type operators, and there's got to be a lot more new Q cohomology classes. So the question is, what do they look like? Well, let's try. So let me give you one simple example. If you take SYM theory, consider a fermionic letter. It could be, for example, partial z psi, for instance. You can set z to 0 at the end. Doesn't matter. Now, if you have a fermionic traceless n by n matrix X, it turns out that it's a trace relation of this form. You can verify this. Trace x to 2n plus 1 is some multi-trace expression involving x. Now, let's consider an example. Say if x is partial z of psi, this thing would vanish in the SYM theory, but would not vanish when the rank gauge group is bigger than this n. But this guy is Q of this operator, which is partial z squared psi, partial z psi to n minus 1. So you might say that, aha, here I will find a new Q cohomology class due to this trace relation, which is represented by some operator that involves this guy here. Unfortunately, that doesn't work because there turns out to be also a trace relation of the form for, in this case, for x to y fermionic n by n matrices that trace x to the 2n minus 1 times y is a multi-trace expression. And it turns out that you will not, because of this, you will not end up finding any new Q cohomology class of this form. So we tried a few different things and failed each time we tried. Then we resort to a computer test. What we do is the stupidest possible thing you can think of, that is to actually enumerate Q closed operators and Q exact operators by writing down all the products, the traces of these operators in component form using Mathematica and check which are the, find the linearly independent ones and see what are the Q cohomology classes compared to the ones that are of the multi-graphon form. This test is extremely time consuming, as you can imagine. But as far as the examples that we have tested, no new Q homology classes are found. Here's a sample of what we actually did. For example, we can test this for SU2 and SU3 gauge theory. Here, I'm talking about operators that could be, these may not be single trace operators, it could be multi-trace operators. They're made out of these, of the shape that I described before, products of derivatives acting on psi with vector z and theta, and eventually set z and theta to 0. The number of partial z's and number of partial thetas are unchanged by the q action. So these are some set of charges that a set of 5 charges you can use to label these Q cohomology class. So for example, let me just guide you through this first line here. So these are operators that involve 4 partial z plus, 4 partial z minus, and no partial thetas, acting on number of psis. Now, each time you act on the operator with q, you increase the number of psi by 1. And you have to start with at least 2 psis because we're talking about SU gauge theory. So you have to at least have, you cannot have trace of psi, you have to have trace psi squared with derivatives acting on them. So this is our 2 psi, 3 psi, 4 psi until, the total number of psis can be no more than the total number of derivatives. Otherwise, this whole expression will just vanish when you set z and theta to 0. So here you have a set of 7 numbers that label the number of Q cohomology classes in SU2 n equals 4 Subrameo's theory with 2 psis or 3 psis, 4 psis, all the way up to 8 psis, which is the maximum number you can have. And you can compare that to the number in the n equals 3 case and in n equals infinity case. You will not know just by staring at this chart whether these cohomology classes really are of the multi-graviton form or not, but indeed we have verified that they're all of the multi-graviton form. And you can go to some higher levels, but the computation becomes more and more time and memory consuming, and we have not been able to proceed much further than this. And you can also, let me just comment on that, these cohomology classes, of course, contain much more information than just the index, because the index will just count, say, add up these numbers with alternating sign, and here you see a lot of cancellation, but of course, there are a lot more number of BPS states than just the coefficients in the expansion of the index. Okay. So for SU2, instead of SU3, you can go to a little higher, but once again, but still you don't find anything new. So being the experimental physicist I will go ahead and make a conjecture that there are no new Q cohomology classes, and everything, all the 116 BPS operators are of the multi-graviton type, which are products of this guy. If the conjecture is correct, it would imply that the number of 116 BPS operators of a given conformal dimension in SUN theory can be no more than the number of such operators in infinite n limit, which count free gravitons. Number of free gravitons grow like the entropy of free gravitons at energy E grows like e to the 5/6. This bound would not be too useful if the energy E is very large compared to n, but one can independently derive a bound on number of such operators at finite n, which says that entropy is less than or less than n to the 1/3 energy times energy to the 2/3. This was the same bound that was found in the scalar sector in the paper of Grant, Grassi, Kim, and Miwala. In any case, with either bound, there's not enough state to account for the entropy of a black hole, which has a property that when energy is of order n squared, the entropy must be also of order n squared. Just as a mathematical aside, our Q-cohomology classes are classified by the so-called relative Lie algebra cohomology with trivial coefficients. Here, for those of you who know what this is relative Lie algebra cohomology where SON is regarded as a subalgebra of this thing I call Gn. What Gn is the Lie algebra of traceless n by n matrices with coefficients that are polynomials of 2 bosonic variables, z plus z minus, and 3 fermionic variables, theta 1, theta 2, theta 3. And this Lie algebra comes with, this cohomology group comes with a natural grading, which agrees with a grading, which a number of degrees, which is the degree in psi in the expression I wrote before. And our conjecture amounts to the following statement, that there's an obvious inclusion. So if you reduce from SUN to SUN minus 1, the inclusion of the Lie algebra Gn minus 1 to Gn induces a map on the cohomology group in the reverse direction like this, and the conjecture amounts to a statement that this map, I star, is surjective for all n. Now, I have a feeling that there are some experts in Lie algebra cohomology in the audience may be able to embarrass me by the end of this talk by telling me whether this conjecture is true or false, but I don't know. So if the conjecture is true, that's an obvious puzzle. We are not producing the expected Beckmann-Hawking entropy of the black hole. Of course, you may ask, why do I expect to get this just by staring at this gauge theory and weak coupling? Well, first of all, there seems to be no reason for this number of BPS operators to jump in this particular in n equals 4 super-Yang-Mills theory. At least I don't see evidence for this. There are a few possibilities. First of all, of course, it might be that the conjecture is false. Maybe we didn't do this computer test to high enough level in the SU2 and SU3 examples. But at least in the SU case, I think we've gone to a reasonably high level and find it kind of unlikely for this possibility to be true. But in any case, it might be possible to prove or disprove the conjecture by analyzing the Hoshio-Serra special sequence associated with this embedding of the Lie algebra, which is a technique that allows you to analyze this Lie algebra cohomology, the relation among these Lie algebra cohomologies. Possibility number 2 is that maybe the number of 116 BPS states just jump as you increase the coupling. That would be a fascinating possibility, but I see so far no evidence for this. What I think is the most likely possibility is that these 116 BPS black hole solutions in supergravity do not actually exist in string theory. For example, it could be that if you take account of alpha prime corrections to the equation of motion, these solutions are no longer supersymmetric. Be interesting to analyze that, but these solutions are fairly complicated, so it would take some work to understand if this is possible. In any case, the existence of the solution just in the supergravity regime implies even if there are not so many exactly 116 BPS operators, there should be a large number of near, very close to 116 BPS operators at dimension of order n squared, and now a strong 12 coupling. And that's a very interesting possibility, and there has been some work by Berkuz and Reckman on this some years ago, and I think this is a fascinating regime in the operator spectrum of n equals 4 super-Yang-Mills to explore. And I'll finish my talk here. Thank you.
I think we have time for one question. Gary.
Could you remind me about these 1/16 BPS black holes? So I know in pure ADS, in ADS, the supersymmetric black holes have to be rotating. Are those the ones
yes.
you're thinking
So
about?
these can carry both SU left and SU2 right angular momentum. Indeed, they generally, so generally there are 5 charges. There's J left, let's say J left 3, J right 3, and then H1, H2, H3, the 3 charges with vector SO6 Cartan generators. Yeah. The solution that are known, that was found by Kanduri, Lucchetti, and Real, is a 4-parameter family. And I guess it's not actually known whether the 5-parameter family solution actually exists, but even this puzzle will be there even for the 4-parameter family. I think for a generic solution, we'll have all the charges turned on. So, but only J left enters the BPS bound.
Thank you.
Okay. Yeah, let's thank the speaker again.
Thank you.